Hi everyone, it's me again with another lecture of atoms, and in this lecture we will continue our journey into recurrent neural networks. We will learn a bit more about the training of neural networks and also explore some more modern type of recurrent neural networks that should further advance our skills to handle textual data and natural language. So let's have a look. We start with a brief recap of what we did in the last lecture, and next we introduce backpropagation through time, at least briefly, to give you an understanding of the main algorithm to train recurrent neural networks and to motivate why neurotypes of recurrent neural networks have taken over at some point. We look at GRUs and LSTMs, which remedy specific problems of training recurrent neural networks. And in the last part, we will look briefly into some recent developments in the field and provide a glance at cutting-edge recurrent neural network architectures. So that is the package of our lecture. Let's get going. And in particular, we will start with a brief recap of the last session and then prepare the next part with some considerations on the training of recurrent neural networks, which so far we have left out. So concerning the last session, we looked at sequential data and we introduced text data as a specific form of sequential data. In that scope, we introduced language modeling as one fundamental basic task in the scope of natural language processing, in the scope of NLP. A language model is a model that predicts the next words in a sequence and essentially is a tool that gives us a probability distribution over words, over a bunch of text. We briefly looked at the applications of language models which are omnipresent in our daily lives, on our smartphones, internet search. These were the applications I was highlighting that you also see here depicted. And we then introduced recurrent neural networks as a possible vehicle, as an option to handle sequential data and text in particular. We categorized recurrent neural networks as a type of latent variable autoregressive model where we process input sequences and where we use a sort of memory mechanism that keeps track of the information that comes in each part of the sequence. With every new element of the sequence, we update our memory, which is the hidden layer in this architecture. The hidden layer that exhibits recurrency, that exhibits these cyclical connections where the output of the hidden layer at a certain step in time is fed back into the network in the next step in time. And we did make the point that recurrent neural networks appear at first glance to be very well suited for language modeling. And then in the last part of the lecture, we had a look at how a recurrent neural network could be used, could be applied for language modeling. And you might remember this example with the sentence started as early as 8 in the morning, talking about recurrent neural networks. After a daunting 2 hour, it eventually turned 10 and the course stopped. And the students closed their books and left. That was our exemplary sentence. And we exemplified how this sentence, or this piece of text, is more than a sentence, how this piece of text can be cut into pieces, into individual sequences that we can feed into our neural network. And we have seen that illustrated. And here's a picture again. And maybe you remember that I was acknowledging that the picture in the previous lecture was slightly inaccurate at the output layer. So as promised, I did correct that. And here you see a more accurate picture of what's going on in an RNN-based language model. In particular, what you see is that the change compared to the picture in the last week concerns this bit here. This is the new bit, because I'm saying that an RNN-based language model computes the output distribution for every step t, right? Compute the output distribution for every step t. A step t is, in a language model, a word in our text sequence. And if we compute the output distribution for every step, that means that we compute a predicted word, a predicted next word for every word. So if I feed the neural network my x1 here at this point, this network gets projected onto the hidden layer, where it is combined with the previous state of my hidden layer, with my memory, which was somehow initialized to have an initial state HO. So my input x1, embedded as E1, gets combined with my hidden state HO to give me the current hidden activation H1. And then from H1 we pull an output by multiplying the latent state, the hidden state H1, with our weight matrix connecting the hidden state to the output layer WHY, and that will give us a distribution over words. And note these A and these ZU, which are to indicate that our output layer has one unit for every word in our vocabulary. And our neural network gives us a probability distribution over these words, and then we can compare this probability distribution to the actual state of affairs, in other words, to what really was the next word in that sequence. And considering x1, the next word in that sequence actually was the word course. And then we can compute some loss. That was the end of last week, and we'll take it right from there to further elaborate on this way of calculating the loss. I created this little animation to really give you a detailed picture of what's going on. So remember, when we work with RNNs, our data is sequential. We have this sequence of words. The course stopped and the students, but we feed this sequence to our network in a stepwise manner. So we feed the network the Z, which gets embedded, then gets combined with the hidden state HO. So we have, using our update equation, a hidden state H1. We pull an output from that and get Y hat 1. Y hat 1 is a probability distribution over all the words in our vocabulary. And then we calculate the loss. And since we have a multi-class classification problem, every word in our vocabulary represents one class, and we are trying to predict the next word, so the right class that corresponds to the input the. And if we assume that our target labels, the actual labels, our Y, is words one hot encoded, so we basically compare our output Y hat 1 to a one hot encoded vector that is all 0, but for one place, and this one place is the place in our output vector associated with the word course, because course is the next word in our sequence. And remember, using the cross entropy cost function to train our neural network, essentially our loss, so J, that's a funny J, sorry about that, J of W, well, essentially is just essentially really it's just the minus of the log of y hat 1 at this point. Why is that? Because, well, we multiply that with y1, which I said is a one-hot encoded vector with a single element being 1 at the place of the word course. Normally, if we make this a bit more general, we write it down as yi and y hat I using some index, or in my case, I should better use the index t, and then we would sum that over all the words in our vocabulary. So let's say we have an index v, indexing the words in our vocabulary. We would have ytv. It's maybe time to grant me a little more space. So we have y t comma y times the log of y hat t comma v. So this index v is to represent our vocabulary, where we have like 30,000 words, and in theory you would sum over all these words, always taking the corresponding output y hat ty and multiplying with the target. But the target yty, remember, it's one hot encoded, so this is 0 for all but one element, and therefore I was saying that essentially it's the negative log probability of our y hat at time point t that gives us the loss. So make sure you understand this negative log prop, of course, and why here at the first step our loss is the negative log probability of the word course, because only the model prediction that corresponds to the word course in our vocabulary, only that probability, the probability of course being the next word, which the network predicts, matters. And the network predicts that probability alongside all the other probabilities for all the other words, but these do not matter because the actual target y or yv is 0 for all the words but the word course, and therefore it doesn't matter. Right, and this gives us a first value of the loss, and then we continue. We now have h1 and a loss value associated with step 1, and then we feed the network the word course to get a hidden state h2, from which we pull our next prediction y hat 2, and y hat 2 will serve us in that we can calculate a new value for our loss, which then by the same logic corresponds to the negative log probability of the word stopped, because stopped is the next word in our sequence. That's the target word if I'm trying to predict the next one. So it's the negative log prop of stopped that we get as our second loss value. And it continues in that manner. The course stopped ends, so ends the next target word. If we feed our neural network the word stopped, we want it to predict a high probability for the word end to follow the word stopped, because this is the next word. So it's the negative log prop of the word end that gives us the third loss, and so forth. So then we have the log prop of the, which captures the loss at the fourth step, and finally students. And then we feed the neural network the word students. Again, we get an output distribution, a forecast. The forecast is probability distribution over the words, and whatever is the next word in the sequence. I put applauded here just to be funny. Haha, I feel entertained now, please. That gives us the final value of our loss function. And the point of this animation is to say, if we feed our recurrent neural network this sequence, the course stopped and the students, in a language modeling context, we get 6 values, 6 losses, 6 loss values from that sequence. And then the final loss is just the sum of these. So in general, we average, or we can average the loss over the different time steps to obtain a total value of the loss. And this is not much different from what we did before. In feed-forward neural networks, the computation of the loss shares many similarities, just that in the feed-forward case, we assume our data to be IID, independent and identically distributed. And we know that here in this example, the input data is not independent. The occurrence of the word course is not independent of the occurrence of the word stopped, because they both occurred in the same sentence or in the same sequence. And therefore, we aggregate our loss over this sequence of inputs, which we believe to be not independent from one another. Right? So that makes sense. I hope you agree. And you know what happens once we have completed the forward path through a neural network and have collected our loss information. We basically feed back this information of where the network did not predict the right target. We feed back this information to adjust our weights. After all, the weights, the weight connecting the input or the embedding layer to the hidden layer, WEH, and the weights connecting the different, or that govern the update of the hidden layer, WHH. And lastly, the weights that connect the hidden layer to the output layer, WHY. They together are the 3 parameters in our recurrent neural network, and they determine its output. And consequently, they also determine the loss that we just calculated. And now we feed back this loss information into our neural network in the backward path to update these weights. And the green arrows indicate the gradient flow during the backward path. And first of all, that's not different. That's not any different from backpropagation in an ordinary feed-forward neural network. Considering the arrows shown so far, we have our loss function, jt, which is a sum. And for every step in time, we can just, in the derivative, we will just have the individual loss values here. So we could write down, well, first of all, we can write down that what we really seek in the training step is the derivative of j of w Unfortunately, my PowerPoint is behaving a little bit funny right now. Probably I'm not allowed to draw too close to the border. Sometimes that happens. A little bit annoying because I do need a bit of space, but let me try here. Okay, seems to work better. So we seek the derivative of our loss with regard to w. That's what we need to do gradient descent. Okay, and what we've depicted here so far is essentially we've calculated the network output y hat, and this y hat, or y hat t, at an individual step, it governs the loss. The loss is a function of y hat. So we can note that down. That's equivalent to applying the chain rule. The derivative of our loss function, j of w, with regard to y hat. That's what we did before. And if you think about it, in this case, our y hat, it is a probability distribution over words. And you know how to get this probability distribution using a softmax layer. And it's not explicitly shown here in the graph, but you should know that if I want my network outputs to be probabilities, then I do need the softmax function. So the y hat, in fact, it is a result of us computing a raw network output, which is h2 times w hy plus the bias plus by. That's how we calculate the raw output. And if we maybe denote that by O, I need a new symbol. Let me use the symbol O. If I have O equal to ht times w hy plus bw, then this is basically what I have here at this bit here at the input to our softmax. So here we find the O, and then we calculate S of O to get our output y hat, where S is the softmax. So S, which would then mean that in our derivative, the next step we need in our derivative is actually our output y hat with regard to O. And the first term, the derivative of the cost function with regard to y hat, that depends, or there we need the derivative of the cross entropy loss function. And for the second term, we need the derivative of the softmax. And afterwards, we can continue, because then we have basically in the next step, we have delta O, which in my case was the raw outputs resulting from applying the weight matrix WHY to the hidden layer output. So we have this bit with regard to delta W HY. If we only are interested in updating the weights in WHY, that's all we need. And this is exactly the derivative that we were using previously in backpropagation. And it continues like that. So once we have that derivative, we want to update a weight that is closer to the input. So if we want to update WEH, for instance, we need to continue applying the chain rule. If we seek WEH, we have to take it a step further. So for EH, we here take the derivative of O with regard to H, which is thus the weights WHY, and then we need to continue, because the hidden layer, there will be some activation function, So the next term would be the derivative of h with regard to z. I typically used z. Is there any color I haven't used so far? Maybe this one. We typically used z as the raw input to a hidden layer in feed-forward neural networks. You hopefully remember that. So here in the graph is, no, sorry, that's wrong. Here in the graph we would find z, where that is essentially just et by w eh plus a bias bh. Okay, so we would have the derivative of h with regard to z, and then finally we could calculate the derivative of z with regard to w e h to update these weights. That's all pretty straightforward. Okay, straightforward, many derivatives, but it's just the chain rule. And as long as we are carefully keeping track of the computations, all is well. But so far there was all just vanilla feed-forward neural networks and backpropagation as we introduced it. But we have left out the more interesting part. How do we actually work out the gradient when we want to update the weight matrix WHH that does these hidden state updates? And if we look at the picture, that is more complicated, because here the gradient flow, it has to pass the computational steps that we performed when processing this sequence. Because the hidden state H6, when we calculate the last forecast in this sequence, when we feed the network the word students and let the network predict the next word, then we carry out this prediction using our hidden state H6. And the hidden stage H6, that is a function of the previous hidden state H5. It depends on H5. And H5 in turn depends on H4 and so forth. And this dependence we need to take into account. So the training of an RNN is basically done by backpropagation, but here it involves backpropagating errors over multiple time steps t. And for that reason the algorithm is also called BPTT, or backpropagation through time. And backpropagation through time requires us calculating the derivative of our cost function or our loss function also with regard to the repeated weight matrix WHH. You can imagine that this adds some more complications, and these we will look at in the next part here.